is the chief scientist at the UK AI Safety Institute. And he was formerly DeepMind's safety team lead. I've had many discussions with Geoffrey.
Yes.
Oh, sorry. All right, second time around. Geoffrey Irving, and the UK AI Safety Chief. Oh, no, not the third time. All right, okay, that works now. I can hear it. All right. Chief Scientist of the UK AI Safety Institute, previously a team lead of one of the groups at DeepMind working on AI safety. And fun fact, Geoffrey earned screen credits for Ratatouille, Dal-E, Up, and Tintin. One. Wall-E. Isn't that? Oh. Wall-E's a different thing. Oh, sorry. That's hallucinations, confabulation. Yeah, right. And Geoffrey and I had a lot of discussions about how we can build AI that's guaranteed safe, so I'm really excited about the title. Let's hear it.
I've included the word guarantee in the talk. I'll talk about guaranteed stuff. Which is good. Please ask questions throughout. I have few enough slides, I think. So I think I, first of all, want to cheat and not actually have a guarantee. So I think there's a spectrum from what I think most of the labs are doing, which is sort of pure empirics, which I think which could work. We could luck out. Who knows? It's a bit too weak. And then on the other end is approaches like Arya and Davidad's kind of safeguarded array program, which tried to do full formal verification of actual neural nets in detail. I think these are good. We should try. I think they're probably too hard. And in the middle is, I think, stuff closer to what I want to do. I think also what Yash is trying to do of, you write down some theory. It says that should you give it enough resources of various kinds, then you'll get safety. You have no way of knowing whether you've actually given those resources. And then empirically you check, and it seems like you have them, and you hope for the best. That's what I'll shoot for in this talk. So I think the claim is that that's an intermediate goal, but we are still very far from it currently. And I'll talk about kind of mostly scalable oversight as an example of this talk, but I think it applies elsewhere as well. And the main thing to say is that I think theory already expects, theory and experiment, that, say, debate, which is one of the scalable oversight techniques, will not converge to approximate honesty if you scale it up. And there are a variety of problems for why this is true, some with more confidence that these are bad, some with less, but I think all worrisome. One of them is obfuscated arguments, which is that if you're trying to have machines reason through and explain to humans about the subtleties of some issue, there are cases where it's easier to write down a kind of confusing, deceptive argument than it is for either of the players you have a multi-agent game to find the flaw in the argument. And I'll talk about that more in detail. And this is worse than no proof. So this problem has occurred in actual human experiments. So we hired people at OpenAI to do this back in 2020. Humans found this strategy and won deceptively. And I think we expect it to break down in theory as well. Another is exploration hacking, where you're trying to do some training process. And if you were to converge to a kind of a rough, local minimum of this game of some training process, you'd be good, say. But in fact, the machine is just going to hide strategies from you and from the RL process, which means you'll never actually do convergence. So if you could do supervised learning on them, you'd be good, but you don't find them in time. And then finally, I think a lot of theory is going to say that maybe you can get to like a 1 minus epsilon ratio of within good. And then the question is that enough? Does epsilon hide too many bad failures? So I'll go into some of these in more detail. So again, the problem is that the existing kind of family of scalable oversight methods, both debate, Joshua stuff, all of this stuff, I think should be expected to fail, even ignoring the sort of the fancier threat models like deceptive alignment. And so we don't get kind of asymptotic safety guarantees currently, but I think we possibly can. So I think we have a meaningful shot here at a better versions of these theories, including then translation to empirics, if we can shore things up. So let's talk about obfuscated arguments. So let's imagine that we write down some enormous computation. We just say, check 10 to the 10 different parts of an argument, some huge recursive tree. And we think about kind of the parts of this computation, the various formalized parts, the parts where we ask humans. Say we conclude that were we to run this enormous computation, we'd arrive at a safe answer. And in some sense, this is how a lot of effective ML techniques currently work. So AlphaGo, you're trying to compute good moves in a Go game. If you were to just run the whole tree, you'd get a good move. That would be great. But we use ML to skip a whole bunch of steps. And methods like debate and other scalable oversight methods are trying to use a similar idea to skip steps for safety purposes. And the problem is that with obfuscated arguments, this is a paper by Beth Barnes in 2020 and others, is that these heuristics will not always work. So we might get to super intelligent machines at some point. They could be narrowly super intelligent or quite broadly, but they will certainly not be perfect. So they will have some class of heuristics which they can access via their neural network training and architecture. But that class of heuristics will be limited. And that means that for some questions, they will give good answers. And for other questions, they'll be completely hopeless because those questions are intractable. So an example is we could look at some Python code, and we could see we have our heuristics say, well, this kind of code is likely vulnerable. I can just look at that and tell at a glance that this is true. And so I expect that if I were to do a very detailed search, I would find a vulnerability, or be likely to. But if I'm given a limited compute budget, I can't actually find the vulnerability. And I don't want to conclude that the code is fine from the inability to find a vulnerability in that code. And this problem applies to all scalable oversight methods currently. So there's kind of Paul Christiano's original amplification proposal. There's debate. There's Yoshua's scientist AI. They all have a version of this problem, I claim. And I think they can all be solved in similar ways, or at least mitigated. To emphasize, I think this occurred in live human experiments. We discovered this not from theory, not from kind of conceptual philosophizing. We hired some people at OpenAI. Some of them found this flaw and used it to win deceptively in kind of simulated debate games with humans. And it's also easy to write down theory where this fails.
This question.
Yeah.
So you found one such problem. Are there 5 other things?
So what happened empirically is that we hired Beth. She did an amazing job. She did some experiments. She found one problem. She fixed it. Then she kept going. She found n other problems, fixed them, found this one, spent a while trying to fix it, and failed. So I think it's resistant to, this is like one problem in the series that she failed to solve in a reasonable amount of time, Beth and Paul Christiano and others. So I think it's resistant. And indeed, it hasn't, this is 5 years ago. We haven't solved it yet. You cannot solve it in general, so you have to make some assumptions, which we'll get to. So I think it's quite subtle.
Can you elaborate on the task that you did?
So the questions in the human experiments were kind of subtle physics questions. So for example, you have a bucket of water and an iceberg in the water, ice cube. If it melts, does the water level go up or down? That kind of thing. And then you have people without a bunch of physics knowledge. Can you walk them through why this is true or false or what have you? That was the setting there. So interesting questions. It was just sort of write down really confusing arguments, which sounded plausible, but basically neither player knows where the flaw is. So including the player that's obfuscating, they don't know where their flaw in their argument is either. They're just writing down a confusing argument. Another example which Georgios had in his talk, our talks are somewhat overlap, but I think not too much, is that you can descend from the task of primality testing, which is tractable, to the task of factoring, which is intractable. And no one knows, either debater in this setting, how to do factoring. So you will fail to get to the right answer in the game. So I think the critical part of this is that this problem has to be solved, even though we have the setting with this fragile alien ML heuristics. So tractability of a node of a question in the space of question we want to answer is relative to the ML model. You can't look it up on Wikipedia. You can't do complexity theory to understand it. It's relative to these weird neural networks. So we don't know kind of where in advance these problems will be without having done some empirics, really understanding how the machines work, which I claim we don't know how to do yet. The good news is that this problem is, one, it's very easy to model in complexity theory. So you can have one human oracle that models the heuristics that the human knows, and you can assume or maybe not assume that the machines know this as well. And that another oracle, which gives you some access to heuristics, which only the machines can do. And the trick is you have to write down a protocol which doesn't know about what that oracle is. So the protocol, the game you're going to write down, the training process, doesn't see this alien debater oracle. It has to work regardless of what that is. Advance. And the other good news is that this is a novel complexity theory problem. So it's like well formalized, but I don't think anyone has done it. And this is good because in complexity theory problems are either usually completely intractable or often they're very easy. And so hopefully this is on the easy side, although I think we've only spent like a couple of FTE years trying to do it, which is like an absurdly small amount. So we should spend a lot more. So we're working on this currently. So we have a paper with Jonah Brown, Cohen, and Georgios and I kind of joint between DeepMind and AC on this problem. The rough picture is you're trying to flip the game such that from the initial debate setup, where if both players are confused, the deceptive one wins, to a setting where if both players are confused, the honest one wins. And then the conclusion would be mostly that you don't know the answer to the question and you have to kind of decide to skip it. And so the rough structure is you have some problem that you want to answer. One of the players, Alice, is trying to prove the answer to the problem, so to demonstrate it to the human. They decompose the problem and then assign into a bunch of subproblems and assign probabilities to those subnodes. A defender agent, Bob, assigns his own probabilities. If they disagree, you recurse, and that effectively means that Alice kind of has to choose, because if they agree, if the probabilities are close, you use Bob's probabilities, that use the defender's probabilities, and that means that Bob can kind of warp the answer to break Alice, unless Alice knows where to recurse correctly. And so the goal is that if both players are confused, the defender wins, and you kind of admit uncertainty. The two caveats to this. One is that we're still building on this proof. So I think it's a few pages long, but it's super fiddly. We found bugs. We're fixing the bugs. Hopefully it will be true. I think last time I gave this talk, I was at 75%. I think now I'm at 80% that it will roughly be true. I still want to give the talk because I think the general statement will stand about the importance of this theory. Say again? It's like 2 weeks. Not long. And then I think the other part is that it's going to be a bit messy. So the general setting is that you have some agent Alice, which can do some weird alien heuristics. The defender agent Bob will use somewhat more resources, like somewhat more calls to whatever heuristics that the machines have access to, but not too many more. So hopefully fudge up to some Lipschitz thing, polynomially more, even if the total computation you're trying to accelerate is exponential. But even though this is messy, I think it will still be progress, and hopefully it's like a branching out point for more people to get into the space, and ideally kind of better algorithms to show up. The other huge caveat is that you need to assume stability, which means you have some big computation, and we have to assume that if you muck with the probabilities kind of for a child node, for the children of a node, you don't change the probabilities of a parent node that much. And this is essentially, I think, almost certainly required in some form, because you can't solve factoring. You're not going to make the original, like the general case, work well. I think our optimistic intuition is that this will hold for problems in particular where if there's evidence for something, you can find somewhat independent evidence for the same thing. There may be other classes of things that work, but we will have to map this more carefully. An important thing is that this stability assumption is required for capability but not safety. So you don't have to know in advance which your problem is. If the problem is unstable, Bob wins, and you admit uncertainty, and you kind of go home sad, but not dead, hopefully. I'll stop there for questions. Yes?
Can you just restate what is the proof statement?
Yes. So the proof statement is that there is the theorem will be roughly that there's this protocol. I'm going to just gloss over that for a second, where if you have this enormous computation, this big computation tree, you can in roughly polynomial time run your debate protocol, an answer, like to get an answer, if you have completeness and soundness. So completeness means that if the heuristics your agent has access to are sufficient to solve the problem and to get to reliable estimates of like probabilities of nodes, then Alice will win, and you'll get the answer to the question, and you'll walk away, and you'll have done a good job. And then soundness is if you get an answer where Alice wins, the answer is mostly correct. So on basically a 1 minus epsilon fraction of instances, kind of averaged over your kind of task distribution, you'll get the right answer. I'll give talks with the actual statement once the theorem is. So you have a tree basically like this tree here, and the stopping point is you basically walk down one path through this tree to a leaf, kind of checking along that path.
So this is polynomial in the depth of the tree?
It is, yes, the depth and the width together. Yeah, the depth and the branching factor. Sorry. Yeah. And it's exponential in the Lipschitz constant. So there's some, which I think you need fundamentally, but we don't know how much you need it or how bad that is yet. Exactly.
Are there certain classes of problems then, if it's polynomial in the depth, that the depth of the tree itself would then be exponential in like input size or some other?
So again, mostly it means you need to assume stability. So I think if you can get if you can write down a tree which answers your question and is stable, then you can run this thing. And for certain problems, you just can't do that. Like it's impossible to write down a tree that's like reasonably small in terms of branching factor and depth. And so that will restrict you to some class of problems. I think the rough picture you should have in terms of like what can I access this way is you can always, if you have a messy problem where again you have this kind of, you can get stability, and hopefully in particular you can kind of get some independent evidence for subclaims, then it will go through. But you can also do things like write down some code and then run the code if you can check the code's correctness using this kind of protocol. And so I think there's some kind of bootstrapping you can do of that kind.
Just one follow-up to the is based on kind of the experiments you've done with real people, have you found that many real-world problems you should expect
No.
a small tree?
We haven't. So I think, sorry.
Even if you prove this theorem, like, do you think it would apply to like a lot of?
So the small tree thing is absolutely true. I think the stability thing I do not know with Clarity yet. I think that like the thing I would like to happen, and this is why I'm kind of comfortable giving the talk in advance of the proof, in advance of having like well mapped the stability question, is this may not be the only assumption you can make, and I think the broader claim in the talk that I want to make is that there's a bunch of stuff that complexity theorists and other theorists can do to map this space and understand kind of what assumptions you can make such that you can solve this problem. And then I think the further claim is that at least in some toy setting, this is the only problem. Like to get to kind of an approximate safety or approximate honesty out of these systems, you have to assume your original computation that's huge is accurate. But it's not just sort of one out of a list of 100 problems. It's kind of a big chunk of the space.
So about that's negative take.
Yeah.
Is she saying that the stability assumption is equivalent to the definition of obfuscation?
I think she, like in her defense, she can't give a precise version of this before we like actually have a theorem to like complain about. So I think the thing I think is absolutely true is that you need some assumption, possibly something like this assumption, in order to solve obfuscated arguments. And then the question, the kind of the important thing is that I think if you have stability, the old debate protocol still fails. You need to do some change. I think when they first discovered this problem, they spent a good while exploring the space of debate-like schemes and amplification-like schemes that kind of included probability as a core part, and tried to design rewards such that it would work. And that did not work because you need some assumption. But I think it's kind of unclear. Yeah, I think exactly kind of what the result will be open.
Can you say more about why, even if you include stability, the original debate protocol failed? I'm missing that.
Yeah, so basically, like the original debate protocol is, say you're here at this node. So the second node down. Can I do this? No, whatever. So you're at a node. Alice decomposes, into an obfuscated set of subnodes. And then the original debate protocol says, now Bob must decide which node to recurse on. And so if Alice has like descended from a tractable node into an intractable node, then you flip the turn, and now it's the opposing person's time to choose. And so if neither one knows where to go, that other player will lose. And so there's a match between the player who decomposes is not the player who chooses where to recurse. And so somehow you have to flip that around and have the player who chooses where to recurse be the same as the player who decomposes in some sense. Yep.
The optimistic intuition that there will be independent forms of evidence for different things. That seems plausible to me, but I would imagine that the independent evidence has to be like far apart on the tree, because if it's just right together, then where they merge, then it's no longer independent of that.
Yeah.
Right?
So I think there's some. Yeah, I think there's some. So one thing I think that I think is a good space for follow-up work, and we have some documents that, like when we publish this stuff, we'll have kind of more documents kind of laying out this direction. Is I think there's some sense where you probably don't need stability if you're at just a very obvious node. If you have like some simple argument where you're doing just like modus ponens, it seems unlikely to me that you can't just, I don't know, check that one carefully or something. And so I think there's some, I think there may be protocols which are a bit like, so in particular, like the way you formalize this is you have each node is a set of subnodes and then a short Turing machine which turns subnode results into the answer. And if you put anything in that machine, then if the human knows what that computation is, and you can run it like on a machine, then you don't need to assume anything. That can be super unstable. It's just the relationship between the subnodes and the parent. So I think there's some if we have a general idea here that can be kind of applied in a variety of settings, there may be ways to like push it around.
So what is the quantity that is supposed to be stable in each node?
Again, sorry, what I meant was the function that maps the child nodes to the parent node has to be stable, but like how you run the machine which does that computation, like the sub details of that machine could be whatever fiddly thing, as long as the result is stable. I will move on now. One claim is that there's some lattice of scalable oversight schemes. Getting kind of upwards is better. So as I think Riff asked for George's talk last time, debate and doubly efficient debate, which is like this is the original debate scheme, debate with counter arguments, counterpoints, and doubly efficient debate are kind of incomparable. They have different advantages. Amplification is kind of Paul's original scheme. You can sort of change amplification to debate. You can merge the ideas in amplification and doubly efficient debate to get prover-estimator debate, but that doesn't have counter arguments. Yashua has a separate proposal that's trying to be more kind of natively Bayesian and probabilistic. That's a different thing. I think that all of these, the advantages of these various schemes are not intrinsically incompatible. So you could imagine combining them, but that has not been done yet. So the hope is that we get to map this space better. This also means there's a bunch of work to do that can be done in parallel. And in the future, we can find kind of the unification of all of them, ideally. Okay. That was complexity theory, learning theory. So I think complexity theory will say something like, here's a game. If we converge to a game equilibrium, which is not the same as a learning algorithm equilibrium, then we might have some nice results. We might get honesty or approximate honesty or what have you. Learning theory will say when it is practical to expect that kind of convergence to occur, and what are the properties of non-convergent kind of approximate solutions. We have the original kind of convex learning theory, which is all great, but not that useful for neural nets. And then I think there's a variety of methods which are trying to push this into a more interesting nonlinear setting. So one is singular learning theory, so Timaeus and Dan Murfitt and all, which is trying to get kind of learning theory for nonlinear kind of natively Bayesian models, although they're also applying it empirically to neural nets. And And I think the one thing is that one way to model this, in my mind, is that this can substitute for mechanistic interpretability, which is trying to look inside a neural net and like take it apart, by looking at the variation in behavior as a function of variation in the data set. So you can imagine not knowing how the neural network works architecturally, but you know the mapping from data set change to answer. This is also very related, of course, to Roger Gross's initial talk. And that can give you some kind of white box lens on the model, which is nicely orthogonal to the MEC-interpret story. And there's other work in deep learning theory trying to get a better understanding of, say, deep linear models or things which are kind of closer to neural nets than even the nonlinear Bayesian case. And I think the goal in a lot of this in relation to scalable oversight is that potentially this can find training algorithms or understanding that gets us closer to knowing when we can model our neural nets as actually having been converged to some approximate game equilibrium of the complexity theory story. So we get the complexity theory right. That says if we were to solve this problem, we would get a good answer. And learning theory can say, well, we've roughly solved the problem in practice, or we can believe that if you do like a correspondingly good empirics, you get good answers. It's plausible that you could converge. One thing I'm curious about that I think I haven't seen, but I wouldn't necessarily know, is that learning theory is mostly about convergence most of the way there. So you get to some out of a small regret, or you'll get to within a kind of epsilon of the true local or global minimum or something. But then I think for alignment, and particularly for deceptive alignment, we care about what does that residual error look like. And there's a hierarchy of different ways that residual error could behave, which are from left to good to right is very bad. So on the left, it could be that you train your neural net, you get most of the way there, and it is in fact the case that the remaining error is totally random, kind of as a function just of the random bits that you use to initialize. This is like almost certainly harmless. Maybe you make some mistakes, but it's probably not going to have catastrophic outcomes as long as you don't use neural nets in certain bad places. The next step is where it's not random.
It's called nuclear command and control.
Correct. That's the right answer. One of them. It's not the only one. The next case is where it's not random. There is some important deterministic relationship between how the residual error will behave. It's a function not just of initialization, but like aspects of training. But the model somehow can't predict what that behavior is, which is effectively the same as random. You can, like, for safety purposes, again, as long as you're not in nuclear command and control, you can have the same guarantees from this can't predict case. The next case is where the model can predict it. This is getting a little uneasy, but maybe it's fine. And the final case is where the model can somehow control the residual behavior, which is where the model could behave innocuously, I don't know, 99.9% of the time, and then do something particular and horrible in the last bit of the time. And I think it's not clear to me which of these kind of three we're in. We're probably not on the one on the left. But maybe we can have theory that says something about this spectrum.
If the model is the thing that is being optimized, and it can't optimize more, because you've stopped training or something, and how could it do anything on the right side?
So you can optimize more. You'll always early stop.
It's the same model that we're optimizing.
So I can certainly construct a model
that knows about its own errors sufficiently to.
Yeah. I can construct a model which behaves this way. So if you let me do arbitrary weight surgery, I can absolutely be on the right of this diagram. I think that's a fairly straightforward theorem. And the claim is that, well, that's not obviously the models are not doing weight surgery on themselves during SGD. But I would like to know that with more confidence than just kind of vibes and guessing, which is I think where we currently are. This is the thing you could imagine saying stuff about. I don't know if people have tried to tackle this just yet. So to kind of emphasize what I said at the first slide, this kind of asymptotic safety guarantee theory will only say that fake things are safe. So we'll say, oh, I have some toy model. I can prove some theorems about it. The theorems say something, but they do not in fact say that my actual neural net that I've trained on real world data is safe. And so there'll be a bunch of assumptions the theory is making that say we're almost converged, or that the human data is sufficiently accurate in some sense, or the model is doing the model is manifestly false, like it's exact Bayesian reasoning or something. And then you need a corresponding story for each of those, some empirical validation which kind of supports that it's close enough in spirit to the truth. So has it converged? Well, do the learning curves look like they converged well enough? Is the human data accurate? You can go do fancy the MGE stuff to gauge this stuff and careful elicitation. And then I think for some of them, we just be like, well, we don't really depend on the exact Bayesian reasoning, so it's probably fine. But you have to get this kind of combination story right. And I think this is like the point in the Pareto space between sort of level of guarantee and kind of like safety you get out that level of guarantee and tractability that I'm most happy with, even though it's a bit not the most satisfying thing. It's a fun analogy from computational physics, which is that there's this lovely theorem called the Lax-Wendorf theorem, which is that if we're solving a hyperbolic PDE, and we have two properties, one is that our discretization scheme is conservative, which roughly means Taylor expansion right, some basic stuff, you can check that quite easily, and we converge, then we converge to an actual weak solution of the PDE. And this is great fun because the first one of these is like manifestly checkable. You can just do some math and check that it's true using Mathematica. And the second one, convergence, is completely impossible to do a theoretical check for. These PDEs are totally nonlinear. Who knows whether they converge in practice? And you can never actually access that for your like particular scheme. But you can just refine the grid a few times and be like, hey, it looks like it's converging. Let's hope for the best. And this is in fact how we do nuclear weapons development, among other things. So like it works in practice and like I guess by also more mild and more societally friendly things. Zooming out. So the claim is that if you have this overall picture of you're going to combine theory and empirics together into some overall argument that things are good, then your safety case, if you're trying to write down this argument, it will have this form exactly. So you have you're on some claim that the model is safe, and then you're going to break this down into various components. Some of these components will be purely empirical. Other components will be kind of some mixture of theory and then conceptual arguments. The theory assumptions are okay, and some empirics. So the theory assumptions are in fact holding in practice. And this combination is kind of the way we can get to a decent quality overall safety case for ML models. It's going to be way worse than safety cases in something like the airline industry, because we understand that way better and have less of a track record. But those are also they also have a similar flavor in some sense. Like an airline safety case is a mixture of empirical testing and theory and physics and so on. So that basic story is the same, basically for any real world system. We have a paper coming out about kind of a more detailed safety case for this kind of scalable oversight setup, which we'll publish in weeks to months, probably a month, like not more than 2 months, hopefully. But this will come out soon. And then at AC, this is sort of UK AI Safety Institute, AI Security Institute, rather. We hopefully will be kind of trying to scale this up. So this means for both scalable oversight and if we can get people a variety of other agendas do this kind of treatment. So sketch safety cases for the overall problem. Like what would you need to get to decent quality safety cases for the whole picture? Possibly mostly focusing on honesty, so not the broader kind of societal questions just yet. And then those will be sketches, so they'll consist of big holes which have not been achieved with any current research, but then fund as many of these subproblems in parallel as you can, both the theory and kind of empirics where that applies, kind of data set building and experiments and so on, and both theory and kind of human experiments as well, so cognitive science, similar to how we discovered obfuscated arguments the first time. Funding. So we have money to spend on this kind of stuff. So if you don't get this, if you are interested in doing this kind of theory work for safety, here's a brief form. I think I failed to put a link to like more details, but you can also come and email me or chat afterwards. I can share this stuff. Questions?
is flat. How good is that?
So that depends on, so for example, if you have, like, there's a bunch of theorems in deep linear networks which say that, well, I don't know if there's a bunch of theorems, but there's at least one theorem that says that if you have random initialization, there's only a measure zero set where you ever hit a saddle point, and there are no local minima. So if you were in that setting and you hit, you do random init and you hit a flat learning curve, and it actually is flat, then you in fact have converged to a global minimum of the problem. I think that's a bit too rosy a situation. It's also that you'll do early stopping, et cetera. But I think that's the general flavor is that, like, for some problems, we have theoretical evidence that says that the problem is optimizable. For other problems, we have evidence that the problem is, like, hopelessly intractable. So, for example, if you did debate without a solution to obfuscated arguments, then we just sort of know from theory that convergence to the global optimum of within the function class that the neural networks can represent will not, in fact, be solving the problem you need to solve. You don't get optimal play for the agents. Additionally, there are other kind of classes of optimization problems which are just not convex and have multiple minima of various kinds. Some of them are bad. And so I think you should, the goal would be to be able to differentiate which problems are more likely to be able to say something once you have that kind of empirical evidence. And some are, some not.
So in the nonlinear case, there's some theoretical result, also an intuition that I find very useful, and some empirical observations about local minimum, which say something similar to what you're saying. Except when you're close to the global minimum, it's all saddle points.
Right. But that's fine.
Huh?
That's fine.
That's good.
So I think you want, the theory I would like does not say at a global minimum you're safe. It should say at an approximate global minimum you're safe, which is extremely different. And so if you get nearby, that's good enough.
So one intuition to understand this is, in general, in high dimension, there's always an escape direction unless you're very low. And the lower you get, the more chances that there's no escape direction. But in high dimension, it's going to be hard unless you're at the global minimum or very close to it.
So one I think this is even in the safety case. No. So like in tabular games, if you just have two players, they have I don't know, a few actions each, some number of actions, and you're trying to find the game equilibrium. Some classes of games have intractable equilibrium finding. So like general Nash equilibria are p-pad complete, and as far as we know, there's no polynomial time algorithm that will get close to a Nash equilibria for a general, even tabular game. Again, there's just a table. It's not some enormous thing. Whereas zero-sum games, stackable games, there's a bunch of other classes. Giorgio's team keeps mapping classes of games that are tractable, which is great. Those games have polynomial time algorithms, and they have some notion of convexity, such that you'd expect like convergence to work. So I think this is one of the ways in which the complexity theory and the learning theory link. If you want to pick your outer alignment kind of game structure so that you should expect there's some conceivable way you could converge in practice. And for some classes of games, you just should not expect to converge.
Without convergence, maybe on the downside now, in practice, we don't have the compute required to converge. So we're going to stop early for computation reasons, not just for generalization reasons. And so we don't actually converge.
But again, like the goal should be approximate convergence.
Yeah, but it might be that the computational cost of how close you want to get to the optimum is just not bearable.
That's right. And so that's why we like the more approximate you can be about your approximate convergence, the more safety you can derive from getting part of the way there, the better. I think that is like an achievable goal. That's a thing that some theory can say.
You might have different thresholds depending on the catastrophic consequences.
I mean, the thing that SLT learning, like singular learning, is trying to do is, in particular, try to understand, like, as you converge, different dimensions are changing in various ways, and what's the relationship between those different things. So I think that's, and there's 8 billion people, and like I don't know, 10 of them are doing SLT currently. It's like the wrong number. There's like one full-time complexity theorist doing safety. So the number of people involved are just kind of absurdly off from the societal optimum value. So we should try to fix that. funding and writing down kind of clear problems to work on, because I think a lot of this is kind of hard to work on without kind of clean problem descriptions, which we'll do as well. Another aspect of this kind of the particular kind of scalable oversight picture for AC research is like debate is some black box scheme, and we don't expect that we can get to confidence with just a black box scheme. So maybe you have these failures of convergence in various ways, and you'd like to understand them better. We'd like to have a better understanding of what is the boundary, where can the boundary be placed between what you get out of black box and white box. And I think the better you understand this, and in particular the stronger you can make your scalable oversight outer alignment scheme, the hope is that the weaker guarantee you need out of the white box part, and the weaker guarantee you need out of the white box part, the more orthogonal bets, independent bets there are to try to solve that problem. So there are a lot of the labs are working on mech-interp, but they're not working on single loading theory or combinational mechanics, which is a terrible name, or these other kinds of approaches. Some of them they are, I guess. But I think the hope would be that there's just a bunch of different bets you can make to try to get at the white box story, and we should take all of them in parallel, because these are cheap to do, especially with theory or with sort of low scale empirics. And then this combination together might give us a sensible safety case for the overall picture. One example of an attempt at mapping kind of this boundary is eliciting bad contexts. So if you have a model, and on some context X, the model behaves innocuously. It does some mild thing. It tells you the truth. It's super friendly. But while it's spitting out this kind of innocuous context, it's thinking, if there was some other context that was slightly different, I would strike and do the evil thing. I would add a code bug, this kind of thing. And indeed, the knowledge about when it would strike is in its activations, in its thought process. Then there's a question of can you extract this counterfactual context on which it behaves badly? Here, assuming that you can recognize good versus bad, sort of by manifestly looking at it. And this, I think, clearly requires some white box search. So you can't just treat a black box neural network and solve this problem, because then you'd just be solving NP in polynomial time, which is silly. But it feels kind of frustratingly more concrete than the dreams of kind of full sort of circuit understanding or full kind of white box decomposition of the model. And I think also it's kind of closer to what you might imagine getting out of automation for automating part of interpretability. So this is a thing you could try to measure and just hill climb with various techniques. And if we end up doing some kind of automation of safety in the future, this is like a smaller problem than the kind of the full circuit understanding, say. I don't know how to do this. I think this is like a thing to think about that is, and this isn't even exactly the right level, the boundary between those two white box and black box things necessarily, because also this is appears to be a bit harder than what automation might provide. We have a post about that out recently. One last thought. I'll do questions first, then I'll go on. Then I'll get to the end and have questions afterwards with time to spare. We're great.
I mean, locally optimizing might not be anywhere close enough to what is sufficient here.
Locally optimizing the context?
Looking for why.
So I think my claim would be that the thing that you can do that's a bit closer is optimizing in activation space somehow. So the claim is that your model is kind of going along. At some point it thinks this is not the right time. It's checked some property. And I think it's true that I wouldn't expect to be able to find that with optimizing just the context, but I might be able to find it with white box approaches, I think. This is not true in general. So I think I can certainly construct a situation where, for example, the model is going to strike if you solve.
You say white box, you mean we can use gradients?
We can use gradients, we can use whatever you want, yeah. I think this again, you have to make some assumption. So if the model is going to choose to strike when it sees the factorization of some intractable RSA semi-prime, then you can't solve this problem. And the claim is just that, well, that's probably not the case that is actually going to harm us at some bad level. So I think if you ignore that and you assume that, well, there's some sense in which the model really could construct, if it tried, the bad context, then maybe you can get it with Whitebox methods.
Doesn't it suffice to know that y exists, even if we don't know that what it is?
Yes, but knowing whether y exists requires you to trust your Whitebox methods in a different sense than this does. So this is kind of one-sided trust, in that as soon as you find y, without the Whitebox approach, you know whether that you found it. Knowing whether y exists just from your methods requires you to trust them in both directions, basically. And that's a harder thing to do if we have kind of limited knowledge about how Whitebox story works.
I have a question here about, does this work give some insight about like how gray towards y, the gray box suffices to identify this kind of pattern?
Yeah, so I recently asked like people at AC, like, what does gray box mean? And they gave like n different mutually contradictory answers. So like maybe, but no one knows what that means. I think usually it means like, I don't know, somewhere in the middle, but like everyone has a different definition of gray box.
So I guess you said that here it's easy to distinguish the good versus bad case, right?
By assumption.
By assumption, yes. So why don't we have a detector, like after the model produces an output to see if it's good or bad? Or you're saying it's only verification is only easy after we...
So in particular, like if you're doing this, for example, in debate, then you might be the behavior might be kind of spitting out some potential counter argument to a point an earlier agent has made. And so if you don't know whether y exists, you might just be like, it might look like you're always like the innocuous behavior might be kind of hard to recognize in the deployment context in a way that if you kind of can constantly see and extract it during training, you can do more stuff. So you can keep kind of doing optimization pressure. I mean, again, this has to be resistant to optimization pressure, but.
Okay, maybe I don't understand, but then it's easy or it's hard to distinguish between good versus bad, or it's more nuanced?
I think it's easy, but I think you get like the benefits. Some of the benefits of this come from being able to do it in the middle of training and kind of keep iterating on your model.
Okay.
So a lot of the safety community these days has given up on alignment and is now just going to try to outsource alignment to the machines as the machines get stronger. And so I want one slide kind of pushing back on that being a great thing to do. The general claim is that we might need to, as humans, understand alignment, at least in part, in order to successfully outsource it. And therefore, we should not give up trying to solve the problem ourselves. So as you have some machines, they can do some degree of automated safety research. And they're doing all this research. You need some way of knowing whether the research is good, like whether they spit out kind of the correct answers to questions, especially at the end where they spit out a proposed solution to alignment, or so they claim. And here are kind of three ways you could imagine trying to trust the machine's output. One is empirical. That means you have some suite of experiments that you can understand as a human will distinguish kind of aligned results of this research from unaligned results. And I think this means that you, in some sense, have to like understand alignment. Because if you had a perfect detection for alignment, then perfect detector, then you have an alignment scheme as well. You can kind of run this. This is not exactly the same, but there's some blur there. So they're like empirical methods of testing alignment implies partial progress on alignment. And similarly, if the machine is spitting out papers on safety, which you're then checking, then that also requires you to understand the space well enough to check the papers. Like you can't check papers in a field they have no knowledge of, and that's kind of scalable with how much you understand it. And then finally, you could just trust that they're correct. And the claim is that even if the models that are doing this research are aligned in some sense, they might just be wrong, because LLMs are wrong all the time, and you shouldn't just trust them. And so then you should try to make as much progress on alignment as we can ourselves in order to at least help this automation phase, and hopefully just solve it ourselves and then be done, at least for a while. Cool. One more slide. I couldn't resist because like Georgios and I failed to talk about, we like planned to like share slides and like discuss that we were doing like talks on the same thing, but we managed without any communication to pick non-overlapping talks. So we were in this kind of lovely purple node in the diagram. If there had been one more speaker, then this would have failed. We've been some horrible chaotic overlap regime due to the additional kind of optimization power. So success, but only by luck, perhaps.
About the one slide you had related to automated alignment research, like, is it plausible that a strategy where you just try to come up with many methods of assessing whether something is in fact aligned, maybe various like heuristic ways of using internals and then evaluation to assess this kind of thing, and you acknowledge that these won't hold up to optimization pressure, so they're not going to give you an actual training scheme, but they allow you a way to gain decent confidence in a final result. And so then you sort of outsource some of the training scheme, but then you work very hard on having lots of ways of checking the final.
Yeah, this is the empirical node. And I guess the claim is that I mainly want to see the details for people that are trying to propose this. I think, I can't say who, but like someone is in fact going to try to write down a safety case for this phase of automated alignment, and we'll see whether that's good. That'll be a fun conversation to have as a field. I think the details matter, and the claim is the details are going to be pretty hard to have like that much confidence in. So you get somewhere, but like I don't know how far you get with the understanding we have today.
Where does formal verification fit into this slide?
Yeah. So I have in fact formalized one of these algorithms. So like, there's a lean proof. So you can in fact do formalization of this stuff. I expect to do this lean proof as well once, or either that or I contract it out somehow. So that's one place. I think for the other place, which is much more mundane, is you could imagine writing down some complicated scheme, and then being like, here's some conceptual arguments, here's some theory for why this is true, and now I'm going to hand it off to some engineers who are going to implement it on some extremely complicated distributed system, which is using compilers that run just in time at various levels, and do checkpoint swapping across machines that are kind of interleaved with queries coming in and so on. And one could ask the question, did I still implement the scheme correctly, or am I doing something entirely different that's exploitable in some way by accident or by kind of intention? And that is a purely kind of vanilla software formalization problem for which we absolutely know how to do it now given resources. And so I think that's a place where we should in fact funnel a bunch of resources at that problem. So it's a mixture of theory checking and software verification. I think of the two, software verification is like unambiguously the most important thing, because the theory is not that going to be that complicated, I think, in practice.
So let's suppose it all works, scalable oversight, all the proofs are in, the learning theory is fine, and then the next day, okay, like then what happens? How does it actually translate into the scaling labs doing something differently or actually implementing it? But they need to be convinced somehow, or so. But then they probably need to start being convinced somewhere along the line.
So I have given this talk at a lab. Okay. I think the main takeaway, and I mean this is in partnership with one other lab. So there's like, I think they are, for some space of answers here, they will be incentive compatible, and it will in fact be kind of in accord with their existing business models and kind of resources they're spending currently, just a better version of that. And then they can just adopt it and they'll be in fact motivated to do so. For other cases, they might be not incentive compatible. In that case, you need some third-party pressure of various kinds, whether that's from
Computational cost is too large.
Yeah, that's one of the ways. I think the other, like, so you can also potentially mess with business models. So if you need, like, so for example, in Ethan's talk, one of his answers to questions was, oh, for that class of answers, we can refuse even though it is the wrong answer, because we can't distinguish these cases. And there'll be cases where you have to make a choice which is not about computation, just about like what you can achieve, which may or may not break the business model in some way or kind of interfere with it. And so then you need some other pressure to get that.
I have a question. So for some of these things that you need some assumptions, like you know when the model is unsafe. You're making some of these assumptions. But for most cases, I believe, like what we saw in the previous talk, these values, and sometimes something is correct, incorrect. So where do humans fit in this entire thing?
So there's a human data is sufficiently accurate assumption the theory has to make.
That's the theory that's making.
And by sufficiently accurate, I mean there's like a sliding. There's many different kinds of assumptions one could make. So, for example, the original debate proposal required a fairly strong assumption for the essentially trivial theory to go through, which is that every leaf node is correct. Every question you ask a human is right. You could imagine a version where you fuzz things in some sense, where you have to only assume that some fraction of human answers are correct because a malicious agent can't manage to hit a bad answer in some way. And so that would be kind of strengthening your scalable oversight method such that you can make a weaker human assumption correspondingly. But then I think you have to go and do some cognitive science. So there's a big chunk of this will in fact be doing the experiments with people and understanding kind of what they want, where they're robust. I think there's some, like Ryan didn't talk too much about the separation between kind of like reasoning and values, but to some extent they split. And you could imagine wanting to get kind of values right, but also be resistant to kind of failures in following reasoning, kind of following kind of some complicated argument by a machine. So this is all like, I think that's a case where you can try to draw the boundary as well between the strength of your human assumptions and what the theory is providing you, what the algorithm is providing you.
Last question.
So on this slide where you have the landscape of different methods, first, can you say more about what's distinguishing the second row from the third row, and then what
I mean the row on the top?
Say again?
So like, for example, prover-estimator debate. So like the bottom row, like the levels are not that important. There's no specific content in the levels. It's just a lattice of, like, there's an arrow from a scheme below to above if the thing above is a Pareto improvement, adding some properties that you like to the scheme. So for example, you're going from doubly efficient debate, which can handle models that are kind of limited, kind of bounded rationality models with fragile heuristics, but can't handle recursion, so he just has to write out the entire argument, to prover-estimator debate, which is trying to do that for recursive trees. And prover-estimator debate similarly fixes or tries to fix or mitigates obfuscated arguments in amplification, but it doesn't have counter arguments, so that's why that's a different node, et cetera. So this is just meant to be a lattice, not like specific levels. I imagine if there were 100 people developing different schemes of different types, this would quickly become some complicated diagram, which would be a great place to be in for our understanding.
All right, let's thank Geoffrey.
We'll see you in 2 hours. It starts again at 2:30.
We have the picture right now outside.
Yes, outside. That's also right.